folks, welcome back. Today I'm going to be completing part C of homework 2 for process dynamics and controls. To get started here, we're going to find the time-dependent heat diffusion equation for a uniform bar with constant thermal diffusivity. So, to get started here, we're going to look at a specific section of this bar, right here. We're going to observe that our Qin Q out is the heat transfer in and out of that specific section, meaning that our Q net is going to equal our Q in minus our Q out. And if we take into account that at this position along the bar we're at position X, and at this position we're at delta X plus X, we can say that Q in is actually our Qx and Q out is our Q at delta X plus X. Subbing this into our equation, we get our Q net is going to equal our Qx minus our Q delta X plus X. Now looking at this, we know that our Q delta X plus X is actually our Qx plus our dq dx, our change in Q over our change in X. So we can sub this in, our Q net equals Qx minus Qx plus dq dx. Obviously here our Qx's cancel, giving us our Q net equals negative dq dx. Now subbing in our Fourier's law for our dq dx here, we can get Q net is going to equal negative 1 over dx times minus k times our cross-sectional area dt, our change in temperature, over our change in x dx, all times delta x. And this is our first equation we're going to need to find our time-dependent heat diffusion equation. So moving on from here, we need to look at another expression for heat transfer, which is that our Q equals our rho Cp times our volume, which we're going to represent here with our cross-sectional area times delta x, all times our u at a certain x time. Now, if we take the derivative of this expression, we get, with respect to time, we get dq dt equals rho Cp cross-sectional area dt dt. And if we combine these two expressions, we can see that we can move our dx over here right behind our cross-sectional area to get another volume, our area times our delta x. So cross these expressions out. To overall get, if we combine these two, rho Cp dt, change in temperature over change in time, going to equal our K times second derivative, change in temperature, change in position, squared. And rearranging this a little bit, we get, to isolate for dt dt, we get change in temperature, or a change in time, is going to equal K over rho Cp, second derivative temperature per second derivative of position. And then again, taking into account that our thermal diffusivity, which we noted was constant alpha, is equal to our K over rho Cp, we get a final expression that our change in temperature over change in time is going to equal alpha second derivative of temperature over second derivative position. And that right there is our time-dependent heat diffusion equation for a uniform bar with constant thermal diffusivity. So moving on from here, we're going to split this up using explicit differentiation into an algebraic expression that we're going to be able to use in Python to model this and get a plot. So let's go ahead and move on to do our algebraic equation with explicit differentiation. All right, so moving on to our algebraic equation, we need to find that using our explicit differentiation. And to do that, we're going to look at our same uniform bar, but we're going to split it up a little bit differently. So for this portion, we're going to look at our uniform bar. We're going to consider our section of interest here to be I. The section following it is going to be I plus 1. And the section preceding it is going to be I minus 1. We're also going to consider our time to be n, so that we could have a certain temperature for our section I at a given section, or at a given time n, accounting for both the distance along the bar and the time at which the temperature at that distance is, allowing us to differentiate this expression into an algebraic expression that we're going to be able to use in Python to model our uniform bar here. So how are we going to do that? Well, we're going to say we know that our temperature at n plus 1 at our section I minus our temperature at time n, our section I, over our change in time from this expression here is going to equal our alpha right here times our temperature at time n at section I plus 1 minus our temperature at time n at section I over our change in distance minus our temperature at time n at section I minus our temperature at time n at section I minus 1, again over delta x, all over another delta x. This makes sense because we've got our delta x squared here, as well as our second derivative of our temperature. So rearranging this into one big expression, we can get T n plus 1 I minus T n at I I'm not going to write out the left-hand side for now. We're just going to say that this equals alpha times T n I plus 1 minus 2 T I at n plus T I minus 1 times n all over delta x squared. Now, if we move some of our stuff over on this side, over to this side, we can get, go ahead and split this up first. T n plus 1 I over delta t minus t n I over delta t. It's going to give us our expression we found over here. So isolating our t at position n, or at position I at time n, we can get t n I delta t is going to equal alpha t n plus 1 minus 2 t I n plus t n I minus 1 all over delta x squared negative out front there, plus our t I n plus 1 over delta t. Now if we rearrange all of this a little bit, we can get our final expression. Our t I n plus 1 is going to equal our t I n plus our alpha times delta t over delta x squared times our t n at I plus 1 minus 2 t I n plus t n I minus 1. And what this expression is going to allow us to do is it's going to allow us to find the temperature at a time following an initial time at the same position based on the temperature at the position following and preceding that position, which is going to be useful for us when it comes to designing around heat transfer in a uniform bar. So let's move into Python so that we can do the following parts, part C for homework 2.
All right, now that we've found our algebraic expression for the temperature along a bar as at a certain time and position along that bar, we can go ahead and simulate the response of a uniform bar that's initially all at 20 degrees Celsius, and then its first end is raised to 40 degrees Celsius, and the other end is raised to 100. We're going to discretize that bar into 50 of the sections we were talking about up on the board, and we're going to show the simulated temperature response for that bar for our R equal to 0 0.499, 0 0.500, and 0 0.501. So let's get into that R a little bit. So when we're talking about this R, that expression is the expression we were talking about up on the board here, our alpha times our change in time over our change in distance along our bar. So I'll just rewrite that out here. I'll copy and paste this expression right up here. And in the beginning case, we said that our R was going to equal 0 0.499. Perfect. All right, so to get started here, we're going to first put our n down, which is going to be our number of sections that we're going to discretize our bar into. So our n is going to equal 50, as discussed up in the problem. And then we're going to create an array of 20-degree, because we know the bar starts at 20 degrees Celsius. So we're going to say that our t is going to equal np dot full of both our n, size n, and then each of the values is going to be 20 degrees because we're starting out at 20 degrees Celsius. So moving on from that, we also know from the problem that our initial t is going to be 40 degrees Celsius from the problem. So that's the first part of our bar. And then our nt, so t at -1, is going to be at 100 degrees Celsius. And going on from there, we can go ahead and create our for loop so that we can plot this out for each of those 50 different segments at each of the times that we're going to have. So let's go ahead and get started with that. So first thing we're going to do is we're going to say our ID x is going to be equal to np dot a range n. And what that is doing is that we're going to plug that into our plot to show the distance along our bar. Essentially, the x-axis is going to be that distance along our bar. So we want it to be an array the size of n, the size of our discrete sections. And then going on from there, we can go ahead and create the beginnings of our figure. So we're going to say figure equals make subplots. And then we can start to make our plot. So the way we're going to do that is we're going to use a for loop. So we're going to say for n in range 5,000. And what that's going to be is it's essentially 5,000 seconds. So our n, as we discussed up on the board, is the top part of our t. So it's our I, which describes where at the bar we're on, and our n is going to describe when it's happening. So we're essentially taking this for like 5,000 seconds. And for this, we are going to go ahead and we are going to plug in our giant expression we put up on here with our t n plus 1. So let's go ahead and that. So to do that, what we're going to do is we're going to say our t going from 1 to -1 is going to equal our, looking up at our expression up on the board here, again, our t going from 1 to -1, all plus our r value, we were talking about before. It looks like the AI is really helping us out here. I believe that's correct. Our r times our t times going from 2 minus 2 times our t going from -1 to 1 plus, oops, plus our t, see up here on the board, at -2. And that is essentially just the code version of that algebraic expression we determined up on the board there. So that's all good. And we need like some sort of counter to take us to the next line. So for that, we're going to do if n% n% 50 equals 0, we are going to do fig dot add scatter, Our x is going to equal our idx. That is our distance along our bar. Our y is going to equal our temperature, of course. Our mode is going to equal lines. And then for our names, it's going to equal a function of t equals n plus 1. Where's our little squiggly bracket? N plus 1. Fantastic. And then I forgot up here, I need to go ahead and add our initial scatter. So to do that, I'm going to say right after our fig make subplots, do fig.add scatter, x equals idx, y equals t yet again, mode equals lines, and our name here is going to be y equals 0, as that is our initial value. And I believe that should be all good. Let's see how our figure looks at 0.499. All right, what's the problem here? For t equals operand. Realized up here I switched my -1 and my 1. So let's go ahead and correct that. Then run all. And finally, let's go ahead and show our figure. All right. Interesting. So somehow I got this upside down. Folks, I think I put a colon where there wasn't supposed to be one, so let's go ahead and run that one more time. And here we go. Here is our plot that we're looking for. So as you can see here, this makes sense. As we begin at time 0 here, the very beginning of our bar is sitting at 40 degrees and the end is sitting at 100, but right in the middle, we're still sitting at 20. And as we progress through time, the entire bar starts to make that straight line of the temperature gradient going from 40 all the way up to 100, assuming both sides are held at that certain temperature. So now let's try out those other R values that we were talking about earlier. So we've got our 0.499. What about 0.500? Let's see what happens when we run that. As you can see, we're still looking all good. The graph looks very stable. But what happens if we add just one more little value to this? Look at that. So you can see here, just adding that 0.001 caused our graph to completely freak out and go unstable. So in the next part of our part C, we're going to derive why this happens, why R values higher than 0.5 become unstable. So let's go ahead and move on to that derivation.
Right. Now moving on to the final part of our part C, we're going to figure out why we saw those crazy oscillations in our program when we had an R greater to 0.5 using von Neumann stability analysis. So, to get started here, I've got two important equations above that we're going to use to do this stability analysis. Add one more here. So we're going to say that T equals e to the I k x times e to the alpha k squared t. Now, if we take this into account for, say, our t, j, n, we get e to the I, k, j delta x times e to the alpha k squared n delta t. Furthermore, if we sub in our j plus 1 and j minus 1, we can get expressions that allow us to sub out this entire expression. So looking at t j plus 1 at n, we can get e to the I k j delta x. And subbing out that j for our j plus 1, we get j plus 1 delta x. And then the second part of the expression stays the same. So we get e to the alpha k squared and delta t. And the same goes for our t j minus 1. And we get e to the I k j minus 1 delta x times e to the alpha k squared n delta t. So moving on from here, we sub this into this and take into note that these two expressions are the same. We can get an even more simplified expression for our tj plus 1 and our tj minus 1. So we can see that our tj plus 1 and is just going to equal our tjn times e to the power of I k delta x. And then you can also see that our tj minus 1 is equal to our tjn times e to the minus I k delta x. Now, if we sub both of these expressions into our expression over here, we get something that looks like this. We get our tjn plus 1 is equal to tjn plus our r times tjn e to the I k delta x minus 2 tjn plus tjn I to the minus I k delta x. If we pull out our tjn, we finally get our tjn plus 1 equals tjn all times 1 plus r times e to the I k delta x minus 2 plus e to the minus I k delta x. And going on from here, we're going to need to sub in a trigonometry equation, our cosine equilibrium, in order to see why our r is going to become unstable when it's greater than 0.5. Here, we can plug in the trigonometric expression that e to the I k delta x plus e to the minus I k delta x all over 2 is going to equal cosine cosine of k delta x. Now subbing that into this expression, we get tjn plus 1 is going to equal tjn times 1 plus r times cosine of 2k delta x minus 2. And then if we specifically look at this expression here, we know that the absolute value of this cosine 2k delta x minus 2 must be less than or equal to 1. And if we remove those absolute value signs, we know that not only is this expression less than or equal to 1, but it's also greater than or equal to negative 1. If we remove this 1, subtract it from both sides of this expression, we get negative 2 must be less than or equal to r times cosine of 2k delta x minus 2 must be less than or equal to 0, meaning that this expression right here must be no larger than 0 and no smaller than negative 2. And what this means further is that r to r must be less than or equal to 1. To simplify this out, if you divide out by 2, we get the expression that r must be less than or equal to 0.5 for stability. And that explains why we were seeing those crazy fluctuations and instabilities in our graph when we had our r bigger than 0.5. I believe that is the finish of homework C for process dynamics and controls.